welcome in 2012. And so we only scheduled a few lunch seminars up to now. And so if you're willing to give a lunch seminar, please tell me or Junha or Mike. And the schedule is pretty open. I'm giving the first seminar of the year. So I will show some first results of the project that we started just last year to constrain, to get global constraints on shortwave radiative properties of ice clouds. And we're not there yet. We don't do global retrievals yet. So I look towards on the title. So I don't have to explain to most of you that ice clouds are very important for climate, and that ice clouds can have a very large radiative effect. And in climate models, we need to improve the representation of ice clouds. The macrophysical properties, the microphysical properties, but also the optical properties need to be improved. So ice clouds are a bit more difficult, or at least different than liquid clouds, because the ice crystals, they're not spherical. They can have a lot of different shapes, and they also span a very large range in sizes. So you have these very tiny ones, which often look quite spherical, almost spherical, and you also have these very large stuff here. So especially for the radiative properties, this is a problem. However, to get the reflection of ice clouds, of clouds in general, you only need basically three parameters, which is the optical thickness of the cloud, and the single scattering albedo of the cloud top, and also the asymmetry parameter of the phase function. The optical thickness of a cloud you can get by integrating the extinction cross-section weighted by the number concentration, and also through the whole depth of the cloud. And for ice crystals are large enough to be in a geometric optics regime, and that means that the extinction cross-section is just 2 times the projected area of the ice crystals. So if you can get an estimate of the projected area of your ice crystals, then you can fairly well get the optical thickness out of it. The single scattering albedo is very much determined by the effective radius of the ice crystals. And the effective radius is defined as the total volume of the ice crystal size distribution divided by the total projected area of the ice crystal size distribution. And as you can see here, this is a single scattering albedo as at a certain wavelength. As a function of this ice crystal, well, this is diameter, it's not effective radius, but effective diameter. And this is for a bunch of different shapes. And you can see that it doesn't really depend on the shape. It really depends on this effective diameter or effective radius. So if you can get the effective radius, you can get the single scattering albedo. And again, so these are it's defined by the volume and the area of your ice crystals, and these are things that you can get quite good estimates about it, and get good estimates in a climate model.
Where do you get the estimates from? I mean, is it based on measurements?
Well, so the volume, the total volume of the ice is related to the ice water content, so in the mass of the total ice, and that is something that is often predicted in models, climate models, also cloud resolving models. The area is something different, but there are estimates of areas of different ice crystal shapes and things like that. So, and often these assumptions are already made in the cloud or in a climate model, for instance, to get optical thickness. So yeah, the effective radius and the optical thickness is something that can be very consistent with assumptions that are already made in the climate models.
But to say that they're good estimates, I think is
okay.
right.
That's where,
Yeah,
that's where I was going with it.
Yeah, that's true. Well, with any estimate, of course, it stays an estimate. But yeah, but at least you're not. You don't have to make so much assumptions about the shape of the ice crystals, and that's different for the asymmetry parameter of the phase function. So the asymmetry parameter is the scattering phase function integrated over the scattering angle and weighted by the cosine. And this is the scattering phase function of an ice crystal. And so at an angle of 0, all the light goes through, goes straight through, and at 180 degrees the light comes straight back at you. So if you integrate this weighted by the cosine, you get a symmetry parameter of 1 if all the light goes straight through, and a symmetry parameter of 0 if basically you have isotropic scattering. And for ice crystals, the asymmetry parameters are around 0.6 to almost close to 1.
Bastiaan, is this for a collection of randomly oriented crystals or one orientation?
Yeah, this is a single scattering on a collection of randomly oriented particles. Yes, and this is actually a hexagonal column, and just fun if you see the shape here. So this is at 22 degrees, and this gives this halo that you sometimes see around the sun. So the 22-degree halo. So if you see this halo, you know that they're ice crystals, and they're of this shape. So they're pretty pristine, and they're hexagonal shaped. But so this asymmetry parameter depends not on volume or area. It depends on the shape, and also depends on the microscopical roughness. So the surface of these ice crystals can be a bit rough. So that also determines the asymmetry parameter. As you can see here, this is asymmetry parameter for a bunch of different shapes, and as a function of size. And you can see, well, it heavily depends on the shape. For some shapes, it also depends on size, but that is because the shape depends on size. The aspect ratios of the components depend on size, and this gives an asymmetry parameter that depends on size. What you see here is the asymmetry parameters for simple plates and columns as a function of aspect ratio and as a function of roughness. So you can see that for very compact particles, with an aspect ratio close to 1, you get quite low asymmetry parameters, and it goes up as you go to more extreme aspect ratios. And it goes down as you go to more roughness. So this asymmetry parameter for ice crystals can range between 0.6 to almost close to 1. And to give an example to how well we need to constrain this parameter, this is just a simple plot showing that the error in the cloud reflection as a function of the error in the asymmetry parameter. And it also depends on the optical thickness of the cloud. So if we have an optical thickness of 5 or so, and we make an error of 0.03 in the asymmetry parameter, we get around a 10% error in the cloud reflection. So just a simple calculation, if we have 342 watts per square meters, and the cloud reflection is around 0.3, then this 10% error in cloud reflection leads to 10 watts per square meter error in the total flux. And so it can be quite significant. And also a paper by Vogelman and Ackerman they estimate that we need to constrain the global distribution of asymmetry parameters within 2 to 5% if we want to constrain the flux due to ice clouds within 5%. So this the constraint is around 0.01 to 0.04 in absolute values. So that's our target. So what is the global view today of these three parameters? So this is the global view of optical thickness of ice clouds, and this effective radius of ice clouds. And you can get these pretty well from instruments like MODIS, using the Nakajima-King method, using visible and near-infrared reflectances. But this is basically our global view of a symmetry parameter. It's a black image because we don't have any remote sensing technique to retrieve this. We have models, again, that range from 0.6 to 0.95 or so, and we have some in situ measurements. And they all show symmetry parameters around 0.75, but there are some issues with in situ measurements. And so it's our main goal to basically fill in this picture. I want to talk briefly about how to get not a symmetry parameter, but the effective radius and optical thickness from remote sensing data. So this is using reflectance measurements in a non-absorbing channel and an absorbing channel. So very often 0.87 for non-absorbing and 2.13 for the absorbing channel. And as you can see here, so these are reflectances in the non-absorbing channel versus the reflectance in the absorbing channel. And these lines here, they are for the same effective radius. And you can see that the reflectance in this absorbing channel mostly depends on the effective radius, especially for large optical thicknesses. So these lines here represent the reflectances for set optical thickness values, and you can see that the reflectance in the non-absorbing channel depends mainly on the optical thickness of the cloud. So if you have a measurement and that defines a point in here, so you can sort of read off from these plots or these lookup tables, you can read off the optical thickness of the cloud and the effective radius. However, these lookup tables that are used to do these retrievals, they also depend on the asymmetry parameter, or the shape of the particle that is assumed in these retrievals. As you can see here, so these black lines are for when I assume pristine particles, so without any roughness, and the red lines are if I assumed rougher particles. And you can see that they're different. And also, if I assume different aspect ratios, these lookup tables are different. So that the retrieval of effective radius and optical thickness also depends on your asymmetry parameter. And as a general rule, assuming a lower asymmetry parameter leads to retrieval of large effective radius and lower optical thickness. So we want to fill in this picture to get all the three parameters, but by doing so, we also want to improve the effective radius retrievals and optical thickness retrievals. So how do we do that? If we look at these images of ice crystals, we see, again, we see so many different shapes and also sizes. And there's and it depends also on cloud-to-cloud basis. So it's very hard to sort of pick a shape or so to do your calculations with. However, if we compare these complex shapes to much more simple shapes, if we compare the optical properties of these two, they often look very similar. So this is, for instance, comparing simulated scattering phase functions and also polarization, so the scattering phase matrix of a complex mixture of bullet rosettes, which are these kind of shapes, and aggregates of columns, so the columns stuck together, but also some columns added in. And so these represent the solid lines here. Let's look at the black solid line here. So this is for a complex mixture. And the dotted line here is when I assume simple shapes. So if I assume a column which has the same mean aspect ratio as the complex mixture, and also the same roughness, so these are pristine. So you can see that they fit pretty well. And also for rough particles, so the solid red line here is the rough complex mixture, and the broken lines here is if I assume just a simple column, and I get very close to the phase function, and especially also very close to the symmetry parameter. And the same is true for the polarization. So if you see, for instance here, this is for the pristine particle. The polarization of this complex mixture is very similar to the polarization of just the single column. So these columns and plates, so these simple particles, can sort of be used as surrogates for the complex mixtures that are assumed to be in ice crystal in ice clouds.
Can you explain how that phase function looks similar? That looks very different to me after scattering angle of 100.
Yeah, this is actually because they are calculated by two different codes. So if you compare columns calculated with one code to columns calculated with the other code, you see the same differences at these angles. However, the symmetry parameter is very similar. So yes, the rough particles, they do look a little bit different in the forward scattering directions, but still especially here, there are no features, and still the asymmetry parameter is very similar.
Oh, I see you have two graphs on one, okay.
Yeah, so the solid black line here is
you're comparing to
you
the
have to
dotted
compare
line.
to the broken line,
Okay.
the black broken line, and the solid red line you have to compare to either the blue or red broken line.
Thanks.
It's sort of it's not.
You don't compare the solid red to the solid
best
black.
picture. Sure. So we also see that the polarization depends on the aspect ratio and the roughness of these ice crystals. So for instance here you see the polarization phase function, so as a function of scattering angle, for a very compact particle, compact column, and you can see it has more features on it than if you have a very long column with a more extreme aspect ratio. And also here you can see the dependence on roughness. So if for a pristine column you see this peak right here, and also you see negative polarization for scattering angles close to 180, and these peaks or these features are sort of washed out if you go to more rougher particles. So what is nice about the polarization is that these features, the polarization phase function, is largely conserved in multidirectional polarized reflectance measurements, which can be made by airplane or satellite instruments. So that leads us so it makes us able to retrieve the aspect ratio and the roughness of these surrogate columns, and with that we can retrieve the symmetry parameter of the ice crystals. So this is then the retrieval procedure. We make a lookup table of polarized reflectances, for these simple hexagonal shapes, so plates and columns, with 50 different aspect ratios and 14 different roughness values. And then we find the best fit to the measured polarized reflectances within a certain scattering angle range. And then the symmetry parameter of this best fit hexagon is our retrieved symmetry parameter for these ice clouds. So this is just an example on simulated measurements. The measurements are simulated assuming smooth, small aggregates of plates, which have a symmetry parameter of 0.85. And the best fit hexagon is a plate, and it has a symmetry parameter of 0.89. So there's a difference, but it's getting close. So we do this for a bunch of simulated measurements. So assuming a lot of different shapes. And so these are made by Ping Yang at Texas A&M. And we have 50 different size distributions, and we also have 3 different roughness values on these complex particles. So what you see here is that the asymmetry parameter of this ice cloud with complex particles. So this is basically the truth. And from the simulated measurements, we retrieve then the asymmetry parameter, and we get a pretty close match. So it's within 5%, which was our goal, and there is some offset around 0.014, but we can get pretty close. So we want to apply this to real data.
Sorry, before you go on. So the food result that you're relying on, where they say complex looking things can be reproduced with the simple ones, is that for a wide enough range of complex things that you feel like it includes all possible ice clouds, or is that for some subset of the?
Well, you always have a subset because there's infinite shapes you can think of. But Ping Yang, they make a lot of different shapes. So that's the most versatile database there is now. And so for these shapes, yes, that's the case. So for these shapes, and this actually shows that if you match the polarized reflectance for these shapes, then you also match at least the asymmetry parameter pretty well.
And so you have a sense that it's not going to turn out to be the case that there are some other Venn diagram worth of shapes out there.
Yeah, of course, this is there's still a limited set of shapes.
Just wondering your own personal opinion on it.
Well, the thing with ice is that it does often contain hexagonal components. And the thing is that anything you make of these hexagonal components will have a similar phase matrix as the component. So, but then they get primed and smashed and whatever. So then you might, or rounded if they evaporate a little bit. So there you might go away from the hexagonal component. Yeah. But actually, we're going to also investigate that.
Is that a reason, Bastiaan, it would be really nice to be able to trust the in situ measurements?
Yeah, I mean, we need validation. So yeah, that's.
So is the Droxel something that has 6-fold symmetry? I don't even really know the Droxel is.
Droxel is I don't have an image right now, but it's a quasi-spherical particle, so it's like a sphere, and then you chop off all the sides to make sort of a Christmas. Yeah. What does it look like?
Looks like a Christmas. But is it a 6-sided? Does it come down to something that has anything six-fold on it?
I think 6-fold and 12-fold, 10-fold symmetry. You know, it's like crystal way to sort of slice it, take whichever symmetry you want, and then they sort of squish them down, swoosh them up.
So it's a good case here because it's a thing that's not a hexagon.
Yes.
And you're doing well with the Droxel.
Yeah. but it does have the edges or so it is, it's not rounded. So that,
But if you're asking, do they do this because it has the same symmetry as a hexagon? No, it's just something that they can calculate, and they use it as a proxy for small things that aren't spherical.
Well, I bring it up as an answer to Jimmy's question, which is it's a thing that doesn't look, you can't reduce a
Right.
Droxel to a plate. If you get a little.
Yeah.
So yes, we need validation, so we apply it to campaign data. So I'm using the RSP, the Research Scanning Polarimeter, which Brian Kent is a PI of. So it's an airplane version of the Glory APS, which we all know was lost in the failure of the launch last year. And it measures total and polarized reflectances at 152 different angles and in 9 different bands, from the visible to the near infrared. So it flies over a cloud and it looks at a certain angle at a certain point of the cloud, and then if it flies further, then it looks at a different angle at the same point of the cloud, and then so you can get, for these 152 different angles, you can get measurements on the same point of the cloud. So an example is shown here. During crystal phase, it was on this airplane, Proteus airplane, which was a little bit of a problem because it was moving a lot and it was bumping up and down. So to really get to the same point on the cloud was a bit of a difficulty. But anyway, so not only Proteus was flying, many more aircraft were flying during crystal phase. So first we look at a case on the 11th of July, and you see these are flight tracks of different airplanes. So ER2, WB57, the Proteus, and the Citation. I'm going to use all these measurements of these airplanes. And I'm going to focus on these two systems, which kind of form here. They're gone now again. But looking at instruments which are on the ER2, this is the picture. So ER2 had a radar on it, so you can see this is the ice water content derived from the radar measurements. And you see that it's sort of a detached anvil from a deconvective cloud. And these are retrievals from the MODIS Airborne Simulator, so it's similar to the satellite version of MODIS, which is on the same platform, same aircraft. So they're collocated, and so this is the optical thickness derived from mass. And this is the effective radius, which is derived from mass. So it's around 20 to 30 microns effective radius. And this is using the old version of the retrieval code from MODIS, which assumes crystals with the asymmetry parameter around 0.8. So if we go to RSP retrievals, shown here, so we apply our retrieval algorithm to RSP. So we can get the same information. We can get the optical thickness from RSP. We also get the effective radius from RSP. We have 2 channels to do it in, and the red channel here, so or channel in red here, is 2.2 micron, which probes deeper into the cloud. So actually, this shows that deeper into the cloud, the effective radius in the cloud is higher. And finally here, this is our retrieval of the symmetry parameter. So we retrieve a symmetry parameter which is around 0.77. So it's very low, and it indicates rough particles and also quite compact particles. So we can compare these mass retrievals with the RSP retrievals. So optical thickness compares very well, and also the effective radius compares very well. Mass is also retrieving effective radius close to the top. So this is, you can compare pretty well with these it's 1.6 micron measurements. So they compare pretty well. But of course, this doesn't give our validation of the asymmetry parameters. So for that, we need some other measurements. And basically, our only shot at that is using in situ measurements, using the SIN instrument, which were given to us by Tim Garrett. And it's on two different airplanes, on a citation airplane, shown here, and WB-57 shown here. WB-57 generally flies higher than the citation. However, as with all the time with the campaign, all the instruments are broken, and so the SIN on the WB-57 actually was a little bit broken and doesn't give us the asymmetry parameter. So in this case, only the SIN on the citation gives us a validation or a comparison of the asymmetry parameter. However, they both get the effective rate, so we can also compare those. So first, just comparing to the effective radius, focusing on that, comparing it to the MODIS retrievals, which compare pretty well to our field retrievals. We see that for the SIN on the citation, it actually compares pretty well. However, the citation is flying towards the bottom of the cloud, which is just not seen by MODIS, which is probably more the very top of the cloud. So so the WB-57 really represents more the effective radius of the top of the cloud, and there you can see that the SIN is much lower, getting much lower effective radius than on MODIS. I will get back to that, but yeah, I think the SIN is off here, but I will get back to that later. So we don't have, for the WB-57, we don't have the asymmetry parameter. It's only for the citation, but this only probes the very bottom of the cloud. But anyway, we can compare those with our retrievals. So this, so in the bottom here, you see the asymmetry parameter from the citation compared with our retrievals. And actually it compares pretty well, but it probes a very different part of the cloud. So yeah, what the asymmetry parameter in the top of the cloud is, that we will know. Again, the effective radius is much lower from the SIN by a factor of 2 to 3. And this factor is actually seen before by Hainsfield and all. And again, I will come back to that later.
Can you explain why there's so little data from the citation?
Oh yes.
Was that the broken
So actually, so here it flies actually under the cloud. So the extinction is basically 0, and it can only get a symmetry parameter when there's enough signal. So only when the extinction is around I don't know, 5 or so, it gets a symmetry parameter. So it doesn't have signal here. It actually is under the cloud. So that gets better actually in this case, where so again crystal phase, and you can see a big storm popping up here, and all the airplanes sort of attacking it as like flies and flying over it, and they're pretty well collocated in this case. So this is our radar view of that system. So it's a very nice, convective cloud, all the way to the bottom, and yeah, it's very well collocated. So measurements of the ER2 and the Proteus. So we can put it directly on the same plot. And so this is showing MODIS retrievals of the optical thickness in black, and RSP retrievals in red and in green. And in green, I scaled the optical thickness to compensate for the fact that they have different asymmetry parameters in the retrieval. So it's most fair to compare green and black, and they compare pretty well. So again, optical thickness is retrieved pretty well. Effective radius, here I can compare to the mass in black, and RSP is in red, using the 2.2 micron channel, and in blue using the 1.6 micron channel. And actually this is a bit confusing because the 2.2 is comparing pretty well. It is a little bit higher, and that's again because I use a lower asymmetry parameter in my retrieval. If I use the same asymmetry parameter, and I did it, I checked it, then I get a very close match of the effective radius. However, I expect actually the 1.6 to be similar or even lower than the retrievals at 2.2, because I expect the 2.2 micron to probe deeper into the cloud, and there you expect higher effective radius. So I don't know what's going on with the 1.6 micron channel. It's acting weird. So let's just ignore that for now. And this is the asymmetry parameter I retrieved using our new remote sensing technique. So we get slightly higher asymmetry parameters as before. It's around 0.78 to 0.8. So again, we can compare it to SIN measurements. And here because it's flying straight through this system, we do have enough signal, so we have asymmetry parameters through the whole cloud. And if you compare these plots, they look very similar. You see the effective radius goes up as you go into this side of the endfall. So it goes up here and also goes up in the mass and also the LSP retrievals. And they're quite flat on the thick part of the system. And also the asymmetry parameter is pretty flat. However, if we plot it on the same scale, then you can see that they're quite off. And again, the SIN effective radius is much lower than the mass and RSP retrievals. And also the asymmetry parameter is much lower from the SIN. So although we have a lot of data from the SIN here, they don't match. And but because also the effective radius doesn't match, we think actually there's something going on with the SIN measurements. And the SIN had some light leak problems and also some calibration problems. But in my view, what's the most probable cause is that there's ice shattering. And with that, I mean that when airplane flies through these systems, it just bumps into the ice crystals and these break up, and they actually, so this is stills from a high-speed camera, and you can see that the ice crystals bump into these probes, and they shatter. So they shatter into small, tiny pieces, and they go into the sampling range. So yeah, this changes basically your ice crystals because it's shattered up in tiny pieces, and because it shatters in small pieces, that increases the projected area of these crystals. And so by increasing the projected area, you basically decrease the effective radius that you derive from these measurements. So that might be one possibility why the effective radius is lower. What that does to the asymmetry parameter is hard to guess. So the SIN is basically for now our only bet on getting validation or comparison. But yeah, these issues have to be addressed before we can really get some real validation. And there are improved probe tips developed, and there are SINs with these improved probe tips. So we hope to get the SIN flying in different upcoming campaigns and compare with our retrievals.
So he can't do, SIN can't do any kind of time of flight corrections to get rid of bursts of particles, right?
No, but yeah.
But because the other people do that, and they get, I mean, when you do the size distribution, you get a much bigger size. So you have a whole nother in situ line of
Yeah, well, SIN doesn't.
logic.
Yeah, it doesn't measure the size distribution, so you cannot sort of.
No, what I'm
use
saying is
that.
like you can attack the SIN from the Heinzfield angle, which is, well, if we look at the whole size distribution, then and you trust a lot of other things, then once again you think that SIN is measuring too small of sizes.
Yes, but because it shatters it up in smaller particles, and these have a larger projected area if you sum them up. So that reduces the effective radius. But yeah, it's
The crystal base that have a good way of correcting the clusters.
Really?
That's the reason they do that 2DS thing. It's higher speed electronics.
So
2D
it's
stereo
but
to
the speed I would think would be a big thing.
but also the stereo, so you can see whether you think you've got multiple particles going against it.
But with this, you also need, the whole point is kind of to get the roughness and the aspect ratio, and in a way you could, it's hard to do that correction on top of the others. I mean, you have no way
it's
to do
basically
that.
impossible.
Yeah.
It might be so if you shatter some crystal, if you shatter it in the components, then like I explained, then the components still have the same phase function or asymmetry parameter as the when they were attached to each other. So it might be that the asymmetry parameter is not so much changed, but yeah, who knows?
Is it
It
possible?
might not. That's the problem.
Is it possible to set up wind tunnel experiments with ice particles of known properties and put your probe in there?
So actually, these are wind tunnel experiments, but they're not done with the SIN. So it might be nice to also do that with the SIN, but yeah, it's not done
I
with
think
the
the
SIN
only
yet.
the only way you would trust, the only one way that you could evaluate whether this SIN instrument is shattering the ice is because it measures extinction. There are also other instruments that measure extinction in an open path where you shine a laser from inside the plane to a corner cube on the end of the wing, and you have a direct measure of extinction, but you don't have any shattering artifacts.
And that's basically also done in this paper by them. And yeah, and they see that the extinction from the SIN is just too high. So yeah, they also conclude that SIN has problems with shattering. So we need better validation of our method. Finally, just very briefly, I want to. So I up to now I only talked about RSP and campaign data, but I promised a global view of asymmetry parameters and also better effective radius and optical thickness, and that we can hopefully obtain by combining MODIS and POLDER measurements. They're both in the A train. Well, POLDER actually left the A train last year, but for a long time they were both in the A train. So they have collocated measurements. POLDER is not like the RSP. It has less angles, but it is an imager, and but it's also less accurate. So I will briefly just show some very preliminary results from combined MODIS and POLDER measurements. And actually I just took what I had from the RSP retrieval and I threw it on MODIS and POLDER data, and I ignore a lot of different things, but it's just to show that the data is there and I can get some signal. So this is just using, this is just showing MODIS collection 5, cloud optical thickness, brightness temperature, and effective radius retrieval. So these are not mine, but they're done by MODIS team. And this is the asymmetry parameter I then derived from POLDER. Well, you can see that it's a very noisy picture. So there's a lot of noise, but however, if I smooth it a little bit, more, we do see some features in there. So, for instance, so you see this very big mesoscale convective system, very high optical thickness, very low temperatures, and on the sides of that you see actually lower asymmetry parameters than on the top.
Where is this? Where
oh yes, sorry. This is the North Shore of Australia. So these measurements were taken during TWP ice. That's a campaign, but these are only satellite measurements. And also we see a lower asymmetry parameters associated with this band of clouds here, which have actually higher effective radius. So we do see some interesting features in this retrieval. However, yeah, we began with a very noisy picture. So we have to deal with it and maybe aggregate the polar data to a lower spatial resolution, and we have to address a lot of other things that are just basically ignored for now. So that's also future work. But first we want to apply it to RSP data, some more RSP data for validation. Again, more crystal phase data, but also from the upcoming Seekers campaign. And I don't think a sim will fly there, but hopefully it might well. But anyway, we get some nice data where RSP is also on the ER2, and also the MODIS Airborne Simulator is also on the ER2. So we get nice collocated data there. And we have to do some more simulations. We need to investigate some error sources using cloud resolving model simulations. For instance, if we have homogeneous, so vertically homogeneous scenes, or also horizontal homogeneous scenes, what does that to our retrieval? Also 3D radiative transfer effects, and like I already said, that vertical structure of the clouds, and also a multi-layered cloud. What effects do that have on the retrieval? And finally, we want to apply to global MODIS and POLDER data. But as I explained, we might need to filter and aggregate the data some more to get rid of that noise. And also there we need some validation. So we need also maybe comparisons with SIN measurements or other measurements taken during campaigns. And finally, one goal of the study is also to advise the MODIS team to what ice crystal shapes and what asymmetry parameter they should use in their effective radius and optical thickness retrievals for ice clouds. So I leave this conclusion and pictures for you to watch, and I will take any questions.
Person to suggest that this should be retrieved globally. Is that correct? Did he suggest that in one of his early papers where he said, "Oh, this is really important"?
Yeah,
or was that
it's
aspect
always
ratio?
been mechanism. It's important. I mean, you need it for your radius transfer calculation. So yeah, from the start, it needed to be assumed.
But was it an objective when POLDER was launched to gather to do a retrieval like this, or?
No. Later on, they became interested in it because when it was launched, it really only had water clouds. Figured it didn't really matter. And then they started looking at the ice clouds, and it was a complete mess. So
less, and do you think you would see less noise with APS-2 measurements?
Yes, I think so. I mean, you also have more angles, so I think that the noise would be, maybe you have sort of waves in the so that instead of straight lines, maybe you have some waves which indicate that there's some problems with 3D structure. So I don't know, but yeah, I think you have less noise, and also the measurements are just more accurate. The noise level is lower.
Well, you could do synthetic retrievals on the same cloud scene, right? Using both instruments. Take the cloud resolving model simulation and do retrievals,
yeah. So actually, I did that also in simulations like this. If I take less angles, just having less angles, that doesn't really matter. So I expect that POLDER, if the noise is reduced, so if it just measures the good measurement but at less angles, then still I can retrieve asymmetry parameter just as good.
I mean, the problem is that once you start trying to aggregate up spatially, then spatial variation and angular variation start getting mixed together.
Mm-hmm.
That would be a problem.
Yeah, that's true. Yeah. But it's already aggregated, of course. I mean, it has a pixel size, so it measures already. Can measure different clouds within the same pixel. That's already a problem.
I can see why people are jumping all over Tim. These effective radii are I admit, like I said, I haven't been quite keeping up with your email exchange. That's insane.
Yeah, these are much too low. And I now have some indication that, so this is a very thick cloud, so very high extinction, very high optical thickness. And this gives a difference, factor 4 or so. And if I go to low optical thickness, a lower extinction, I get factor 2, 3. And now I went to low extinction, even lower extinction cloud, and again, so this line sort of shifts towards the mass retrievals if I go to lower extinction. So that, again, that might indicate that it's shattering problems, because if you have just you bombard it with more ice, you have just more shattering. More questions? Okay. Thank you.